All right, this week we're going to be exploring wave speed. We've talked about how waves travel, longitudinally or transversely, the two different types of waves. We have talked about how waves are a vibration, they have period and frequency. We also mentioned that they have wave speed. And that speed is related to the type of wave and the medium that it's traveling through, by and large. Now, there is a little bit of a caveat to that, which I'll explore at the end of the video, or at least I'll mention. But this week we're going to be talking about how the medium affects the speed of the wave. Now, I wanted to talk about sound in particular. And so sound is a wave. It travels a certain distance in a certain amount of time. That's what speed is. It's distance divided by time. And so if I wanted to measure the speed of sound, one way that I could do that is to take the speed, take a distance that sound travels and divide it by the time it takes to travel that distance. Now, sound is fast. At standard air pressure and temperature, it's about 343 meters per second, which is faster than I can run. But that means we're going to need either a large distance so that the amount of time it takes is noticeable, or we're going to need a really good reaction time over a shorter distance. And so I've explored the speed of sound in both of those ways. I'll share them with you now. One of them, I took this LabQuest by Vernier and two microphones that were attached to it. I put one microphone here on the end of my table and the other one 2 meters away. Now, for those of you in the US, that's about 78 3/4 inches. Whew, can't even say it. Inches! About 78 3/4 inches. Now, I then stood way over there and I made a loud sound, by smacking two pieces of wood together. Now, that sound wave created by that smack travels outward everywhere in spherical direction, right? In every direction at the speed of sound. It reaches one microphone before it reaches the other one, and I recorded 5,000 samples per second on the LabQuest, which means that I was able to see on the graph exactly when the first microphone heard that sound and when the second microphone heard that sound. And there's a delay. And that delay tells me that the time it takes to reach one microphone versus the other. Now, the 2 meters that the sound traveled between the two microphones, divided by the amount of time, tells me that the speed of sound I recorded was just about 343 meters per second, exactly as we expect. That's fantastic, amazing result. I also explored this with my daughters outside, using a larger distance and therefore a larger amount of time. It's less precise, but let's take a look. Alrighty, so it's a beautiful day. Woo, sunny. My daughters are down way over there. You can't even see them. Zoom way in. There they are, right down there. You can't even see them. I'm gonna put the other lens on the camera in just a bit. But we are out here to see if we can determine the speed of sound, because they have a pot and a spoon, and they're gonna hit the pot with a spoon and make a really loud noise. And I am here all the way down the street, as far as I can get line of sight. We'll see. It's a little over like 120 meters, so we should get about 1/3 of a second delay between the hit that we can see and the sound of the hit. All right, let's see if we can do it. All right, they're gonna try it. All right, so I'm not sure if we were able to hear that in the camera, but we'll see when we get back inside. All right. Now, I analyzed it in the time delay between seeing the smack and hearing the smack was about 10 frames, which is about, well, the 30 frames per second. So that's almost exactly 1/3 of a second. Best as I can calculate using just one frame analysis. So that's 1/3 of a second, and it's 123 meters, which gives me a speed of sound of about 370 meters per second. And that's a little fast, but with only frame-by-frame analysis and measuring the distance using Google instead of on actual tape measure, it's the best as I can get. And it's pretty good. It's within 10% or so. All right. We also can talk about waves traveling not through air like sound, but waves traveling on slinkies. Now, slinkies are wonderful toys, okay? They allow you to sort of have really fun noises, right? That's a really nice, satisfying sound. But they also, if you stretch them out, you can send a wave from one to the other by shaking it. Either by shaking it to make a transverse wave, or you can shake it the other way to make a longitudinal wave. Back and forth gives you a longitudinal wave. Up and down or side to side gives you a transverse wave. And so what I've done is I've stretched this slinky out to see how changing the properties of the slinky, primarily the tension, affects the speed of the wave. So we have here a slinky, which is on the table here, and I can create a wave that travels down the length of the slinky and back. It reflects off the end, and we see that I'm making this is a transverse wave, since the motion of the medium is perpendicular to the motion of the wave. Like the letter T, the capital letter T is transverse, it's perpendicular. So this is a transverse wave. Each of the individual coils just moves side to side, but the whole wave travels down the slinky. And we can see the speed of this wave. It goes down and back. If I were to change the medium by making the spring more stretched, then we can see that I can very easily change the speed of the wave also. Notice that it's much faster now. Now that I've increased the tension, I've changed the medium. It's the same type of wave, the same approximate amplitude, but the speed of the wave is much faster because the medium has changed. And so that gives us evidence that the medium of the wave is what determines the speed of the wave. As you can see, the higher tension in the slinky produces a medium that has a higher wave speed. It's the same slinky, it's just we've changed the medium in some way by making it more stretched out. There's more tension there, and so one molecule or one link of the slinky can pull on the next one more quickly, and that makes it snap back into place, and that makes the wave increase in its speed down the slinky. Fascinating. Okay. What I want you to do this week is to explore the speed of a wave in water and change the medium of that water, the depth, to see how that affects the speed of the wave. Now, you'll need a tub for this. Any kind of tub will do, but you want it to be rectangular and fairly long as you get. And as close as you can get to straight vertical sides. That way the distance it's traveling as it gets deeper and deeper, it doesn't change. You'll see what I mean in a minute. But I have a couple of examples here that I just pulled from around my house, just various things. Any of these would do. I'm going to use this one just because it's the most compact and it has the clearest sides. It seems like the best option for me. So I'm going to put these aside. Then what you're going to do is you're going to need some water. Okay? Plain old everyday tap water will work great. What I want you to do is to measure the length of your container. And this one is about 29.5 centimeters is the length of this container on the inside. And so that means that if I send a wave from one side down to the other, it's going to be traveling 29.5 centimeters. And then back, and then back. I can then tell how far the wave travels, and I can use a stopwatch, like on my phone or iPad, to determine exactly how fast it's moving by taking the distance the wave travels divided by the time that it takes. Okay, so I'm also going to need a stopwatch. So let me get out my trusty phone, which has a nice stopwatch on it. I prefer the mechanical stopwatches that actually have a button, but I don't have one of those with me today. So I'm going to have to use my phone, and I'm still timing. It's been 42 days, 47 hours, 9 minutes, and what? That's just, why have I been timing for that long? That's just ridiculous. It's just 42 hours. Anyway, so what we want to do is we want to put in about 1/2 centimeter of water. And if you have to work in inches, that's fine. You could go by like 1/4 inches, would be fine. Okay, so I'm going to put in enough water so that it goes up to about 1/2 centimeter across the bottom of the pan. Okay, it doesn't need to be exact, but close as you can get. And then what we're going to do is we're going to send a wave going down and back by lifting one edge and then dropping it back down. And you can see that wave going back and forth across the surface there. You can see that. I'll cut into a closer view in just a moment. But what we're going to do is time how long it takes that wave to travel back and forth. That's a nice sort of like straight parallel wave that's going back and forth. Pretty easy to time. After about three lengths of the container, it's really hard to track. So why don't we just do, so what we'll do is we'll just time for 3 lengths of this container. Okay, so I've got my stopwatch here. I'll lift one end up, let it settle, and then drop it back down. And when the wave gets to this side, start. 1, 2, 3, stop. That was 3.65 seconds. Okay, so I'd write that down for trial 1. I do it a couple more times, 2 or 3 trials, I'd say 3 trials each. And then after that, I'm going to increase the depth of the water to 1 centimeter, right, rather than ½ centimeter, and repeat the whole process. So this is what I would do. Now, if you don't have a tub like this, or if you can't be bothered, I'll provide some video for you at the link in the description, a video where all I'm going to do is just go through this. I won't provide the numbers, but you can record it using your own stopwatch on the video. Alrighty? So, great. Good luck. Oh, I should note that this was inspired by a video that I saw. I'll link it up here in the little card up the top. All right? Thanks. Okay. I should mention, I said earlier that the medium and the type of the wave are the things that determine the speed of the wave. And that's true for 95% of the speed of the wave, maybe even more. Almost the entire factor that plays into determining the speed is the wave type and the medium it's in. Now, there's a little bit of a difference though between 2 waves in the same medium and the same type that have different frequencies. This is called acoustic dispersion, and Skunk Bear from NPR did a really great video that describes this. And basically it explains why rainbows happen and also why you get really fun sounds if you listen very closely to a slinky. It sort of sounds a little bit like Star Wars. In fact, part of how Star Wars made their sounds was recording something like this, but not on the slinky, on a really big cable. But I'll link that video here for you, okay? Enjoy.